Hello and welcome to our discussion on Kw and pH. These are going to be some of our calculations involving acids and bases and describing numerically what they are. A lot of this should be review from pre-AP. So to start off, let's look at Kw. Kw is our equilibrium constant describing the self-ionization of water. Well, to determine if something is acidic or basic, we first have to have a neutral starting point. That neutral starting point is water. The reason water is neutral is because as it self-ionizes, it produces one hydronium ion and one hydroxide ion. So in that self-ionization process, one of our waters acts as an acid, donating its hydrogen to the other who acts as a base by accepting that proton. The acid is then going to become OH minus, our conjugate base, and then our base water will become H3O plus, or our conjugate acid there. Well, because we have a 1-to-1 mole ratio, we are producing equal amounts of hydronium and hydroxide. Whenever we are in pure water at 25 degrees Celsius, the concentration of each ion is going to be 1 times 10 to the negative 7 molar. That is going to change with temperature. Remember that our equilibrium constant, capital K's, only change when temperature changes. So this is only true at 25 degrees Celsius. Since each ion has an equal concentration, we say that pure water is, again, neutral, and the equal concentration of both of those is 1 times 10 to the negative 7 molar. The equilibrium constant itself, our Kw, is 1 times 10 to the negative 14th power. Let's look at where that comes from. So we know equilibrium constants are products over reactants. For Kw is just going to be our products because they are aqueous. Our liquid is not included in that equilibrium constant. So Kw is equal to H plus times OH minus. We already said that both H plus and OH minus are equal to 1 times 10 to the negative 7. So the product of those, or our Kw, is 1 times 10 to the negative 14. Again, that is true at 25 degrees Celsius. K is temperature dependent. So since we know that our neutral solutions have equal H plus and OH minus, we can then determine if something's acidic or basic depending on which ion is in greater concentration. Whenever we have more H plus, we're going to have an acidic solution, and if we have more hydroxide than H plus, we are going to have a basic solution. Well, Kw is a bit more useful than that as well. If we know the concentration of H plus in our solution, we can calculate the concentration of hydroxide using Kw and vice versa. So let's look at a few examples using our Kw here. On example number 1, the first thing we want to do is calculate our hydroxide ion concentration in barium hydroxide. Well, we know the concentration of our barium hydroxide, but we have 2 hydroxides in every barium hydroxide, so we're going to need to account for that. Taking our initial or our given molarity of that barium hydroxide, we know that every 1 barium hydroxide contains 2 hydroxides, so our concentration of hydroxide will be double the concentration of the whole base. It'll give us 5.4 times 10 to the negative 4 molar for those hydroxide ion concentration. Well, we can also find our H plus using that Kw expression. We know Kw is our H plus ion concentration times our hydroxide ion concentration. Well, we know Kw is 1 times 10 to the negative 14, assuming we're at 25 degrees Celsius. We know hydroxide, so we can just go and solve for H plus. When we rearrange for our H plus, take our Kw divided by the hydroxide ion concentration, or 1 times 10 to the negative 14 divided by that 5.4 times 10 to the negative 4 molar, and that should give us 1.9 times 10 to the negative 11 molar for those H plus ions. So then, looking at if the solution is acidic, basic, or neutral, well, we have more OH minus than our H plus, so this must be a basic solution. For number 2 here, go ahead and pause the video. Take a moment to try these out on your own. Resume when you're ready to check those answers. So here we're given an aqueous solution of our nitric acid, and it has a hydroxide ion concentration given to us here. We're looking for our H+. Well, we know Kw is H+ times OH minus, so our H+ is going to be our Kw divided by that OH minus concentration. So that should have given you 2.0 times 10 to the negative 4 molar there. Part B, though, we're looking for the molarity of that nitric acid. So we have to remember that our nitric acid is a strong acid. That is a strong acid that dissociates 100%. All of the H plus that was in the acid is in that 2.0 times 10 to the negative 4 molar. That's equal then to the concentration of our acid, so we also have our 2.0 times 10 to the negative 4 molar HNO3. Lastly, acidic, basic, or neutral. This is going to be an acidic solution. When we compare our OH minus concentration to that H plus concentration, we have more H plus, making it acidic. So moving on, let's look at the pH scale and the pOH scale. Both of these are another way to express if a solution is acidic or basic. The letters pH stand for these French words that I'm not even going to try and pronounce, but they are translated to the hydrogen power. The P in that is kind of like a multiplication sign. Like an X always means we're going to multiply. That P means we're going to take the negative log. So the pH of a solution would be the negative log. That's what the P part stands for. And the H is for our hydrogen ion or our hydronium ion concentration. We use our hydronium ions and our H3O plus, our H plus hydrogen interchangeably. So we can think of pH equals the negative log of H plus, or pH is the negative log of our H3O plus. And this formula, the pH equals the negative log of H plus, is on your formula chart. So let's look a little bit more and delve into the meaning of this pH scale, which is a log-based scale. Since it is a log-based scale, that means that every 1 unit of change in the pH is equal to a 10 times change in the H plus concentration. However, pH and that H plus concentration have an inverse relationship. Whenever we have these low pHs, we're going to be more acidic. But more acidic means that we have a high H plus concentration. If we look at this from the opposite end, those high pHs are a basic solution. Whenever we have a high pH, which is basic solution, that means we don't have very much H plus at all. We have very little H plus and more OH minus. So we need to recognize two things from this pH scale. There is an inverse relationship between pH and our H plus concentration. And then every 1 unit of change is going to be a change in 10 of the concentration. And then, of course, we need to be able to calculate pH given that H plus ion concentration. Moving on, let's look at the pOH scale. pOH is the negative log. Again, that P part just means our negative log, but this time is for the OH, or the hydroxide ion concentration. So we get this formula here, which again is on our formula chart. So now when we look at our pOH scale here, we can see that our acidic solutions now have a high pOH, whereas our basic solutions have a low pOH. Well, on that low pOH, if it's basic, that means we have lots of H+. We have a big OH minus concentration here. So basic solutions have lots of OH minus, and here it's 10 to the 0 power. Whereas 10 to the negative 14th power, whenever we have those high pOHs, that means it's acidic. Acidic solutions have really low OH minus concentration because they have lots of H+. So we can also see that if we look back at our pH versus the pOH scales here, we can see that we have that relationship where Kw equals H plus times OH minus. If we have lots of H plus, we have a little bit of OH minus. If we have lots of OH minus, we have a little bit of H plus. And so lastly, this is still a log-based 10 scale. So every 1 unit, we're going to see 10 times a change. Let's look at 2 units this time though. If we have a change in 2 units of pH, we're going from 10 to the negative 14th to 10 to the negative 12. That is 100 times the change. So if we had a 3-unit change, it would be 1,000 or 10 to the 3rd. A 4-unit change would be a change of 10 to the 4th power. So again, 2 important things to know. Every 1 unit of change is a change of 10, so 2 units would be 100 change, and we still have an inverse relationship between our pOH and OH minus. Last big important thing, and the best part about our pOH and pH relationship, they will always add up to 14. And you're really looking out here because this one is also on your formula chart. But let's talk about why this pH plus pOH equals 14 is true. It comes back to our Kw. So we know that our Kw is equal to H3O plus times OH minus, and that value is 1 times 10 to the negative 14 at 25 degrees Celsius. Well, we can take the log of both sides. That gives us, so the log of our H3O plus is the negative log of H3O plus. Negative log of OH minus is negative log of OH minus. Our multiplication is going to turn into a plus. Negative log of 1 times 10 to the negative 14 is 14. Well, negative log of H3O plus is equal to pH. Negative log of OH minus is equal to pOH, so pH is equal, plus pOH is always equal to 14. So we've seen 4 different equations that relate our hydrogen ion, hydroxide ion concentrations, pH, and pOH. So we do need to be able to convert or find one of these missing pieces or all of the missing pieces given 1 and using the equations that we know. So first off, looking from H plus to OH minus, that's our Kw expression. Using our Kw expression, we can find one of those missing concentrations given the other because we know Kw is always equal to 1 times 10 to the negative 14th power. We'll look at pH to pOH next because that's pretty simple as well. It's based off that Kw expression, taking the negative log of everything as we just saw, and we end up with pH plus pOH is equal to 14. So if we have one, we can find the other from subtracting by 14. So we saw 2 other equations involving our pH and our pOH. So if we have H+, we can find our pH because it is the negative log of those H+ ions. If we have our OH-, we can find our pOH because pOH is the negative log of our hydroxide ion concentration. Well, that leaves us with one more equation that we haven't seen yet. And spoiler alert, this is also not on your formula chart. If we have the pH, we can find the H plus concentration by taking the anti-log. To solve for H plus from the pH, we would need to raise both sides, looking at our equation here, to 10 to the negative power. That is going to take out our log and give us our H plus ion concentration. So therefore, we can find our H plus concentration given the pH by, again, doing the anti-log, which is 10 to the negative pH power. Similarly, we can find our OH minus concentration by taking the anti-log of the POH, which would be OH minus is equal to 10 to the negative POH power. One last thing before we get in some practice here, let's talk about our sig figs when it comes to our log scales. Sig figs in any log number is just the digits after the decimal spot. So if we take the log of 1.0 times 10 to the negative third, which just has our 2 sig figs, in the log number, our 2 sig figs are falling after the decimal spot. So similarly, if we take the log of 1.0 times 10 to the negative third, we have 3 sig figs. In the log value, that's just the things after the decimal spot. So we need 3 decimal spots to represent those 3 sig figs. Let's look at a few more examples here. Here we're taking the log of 2.25 times 10 to the negative 6. That's 3 sig figs. Well, in the log number, our 3 sig figs fall after the decimal. Taking the log of 0.03, that's just 1 sig fig. In the log number, only what's after the decimal is going to be significant. So there's our 1 sig fig. Well, these guys here, this is doing our anti-log, 10 to the power. So that means that these guys, the power that we're raised to, is our log number. Only what's after the decimal is significant in our log number. So that's going to be 2 sig figs. So our plain old number, normal number, is going to have just 2 digits for our 2 sig figs. Looking at the very last one here, we just have 1 number after the decimal spot. Since that is a log number, we know that again because we're taking the anti-log, 10 to the power. We just get 1 sig fig in our normal number. So here we have some practice. Here we're just doing these calculations to the correct number of sig figs. Then on 5, we want to do some calculations. Let's start with these ones at the top. 1, 2, 3, and 4. Go ahead and take a moment and try out those calculations, getting the correct number of sig figs. Pause the video and resume when you're ready to check. So taking a look at these, once we perform this math in the calculator, our normal number that we're taking the log of on number 1 has 1 sig fig. So in the log number, that 1 sig fig falls after the decimal. Similarly, in number 2, our normal number has 5 sig figs. So those 5 sig figs all fall after the decimal in our log number. 3 and 4, we're taking the anti-log since it's 10 to the power. So this 0.8 is a log number, only 1 sig fig after the decimal. So we get 1 sig fig in our normal number. Again, 10 to the power is an anti-log. So in this log number, only what's after the decimal is significant. There's 2 sig figs there. So we rounded our calculator answer to just those 2 sig figs. Now let's take a look at number 5. We are given a 0.25 molar calcium hydroxide solution and we want to find H plus, OH minus, pH, and POH of that solution. Well, calcium hydroxide is a strong base, which means that for every 1 calcium hydroxide, we're going to have 2 OH minuses. So we have to find that OH minus ion concentration first by multiplying by 2. So since there are 2 OH minuses for every 1 calcium hydroxide, that OH minus concentration is going to be 0.50 molar. Well, we know that given OH minus concentration, we can find H plus using our Kw expression. Rearranging that to solve for H plus, we get Kw divided by our OH minus concentration. So 1 times 10 to the negative 14 divided by 0.5, that gives us an H plus concentration of 2.0 times 10 to the negative 14 molar. We can definitely see that this is a basic solution because we have so much more OH minus. Lastly, we want to calculate our pH and pOH. Remember that P stands for negative log, so pOH is a negative log of our OH minus concentration, which is going to give us 0.30. And that makes sense because whenever we have really low pOHs, that means we have lots and lots of OH minus. So then we can go and calculate our pH similarly, which is the negative log of that H plus ion concentration, and we get 13.70. Remember, really high pHs and pHs above 7 mean that it is a basic solution. We have very little H plus and lots of OH minus. The other thing we could have done to find our pH is our 14 minus pOH, and we can also see that pOH and pH add up to 14. Now go ahead and pause the video using your pH concept map if need be. If you need any of those equations, try out number 6 and resume when you're ready to check your answer. The first part of this, easiest thing to find is pOH. pOH plus pH equals 14, so subtract your pH, we get 6.59 for the pOH. Then when we go and find our H plus and OH minus, we have the pH and pOH, so we can just simply take the anti-log of both. So 10 to the negative pH gives us that molar H plus concentration of 3.9 times 10 to the negative 8, and we can see our OH minus concentration as there as well. The other thing we always need to be thinking about is our sig figs. These are our log values, our pH and OH, so those only have 2 sig figs. Our normal numbers, we need those 2 sig figs as well. So there is our pH calculations and the sig figs. Don't forget about those that you need to be working on. We'll continue practicing and learning a little bit more about KW and pH, pOH stuff in class. Hope you had a great break.